Welcome. Today we're going to be taking a look at the notes worksheet entitled Sum and Difference Formulas Day 1. So at this point for this unit, what we've been doing is exploring the various relationships amongst the 6 trigonometric functions. And we've been doing that by verifying those trigonometric identities. So today we're going to shift gears a little bit and start to take a look at working with the inputs a little. We're going to combine inputs together and take a look at what happens with our the primary ratios, sine, cosine, and tangent, as we go through the process here. So again, what we're going to do is sort of combine inputs together and see what happens. Obviously, you can tell by the title of the notes, today we're going to combine inputs together with addition and subtraction, hence what are called the sum and difference formulas. So there are 4 that you will have to learn / memorize for this particular section here. And typically what you do is start out with the one with cosine and what's called the difference formula for cosine. And as it says on your paper, I do actually have a proof for this. And so if you are interested in taking a look at that, I can kind of walk you through where this formula comes from and so forth. But I will leave that, of course, to your discretion. So let's give you one of the 4, kind of explore that and the types of problems that we're going to be doing, at least initially here. And then the other 3 will come out just a little later on. So this would be what's called the difference formula for cosine. And here what we're doing is combining 2 inputs, 2 angle measures in radians or degrees, or 2 real numbers if we're talking about that angle measure in radians. So we're going to combine them together via subtraction. And of course, once I have that combined input, that new input, I'm looking at the ratios. And of course, in this case, I'm looking for the cosine ratio. And so the way it turns out is the cosine ratio of the combination angle, and that's what I'll call this piece right here, combining 2 angles together to create a third. The combination angle, I should say the cosine ratio of the combination angle, is based on the ratios of the original 2 angles. So it goes like this: cosine of the first times cosine of the second, and then a plus sine of the first, sine of the second. So cosine, cosine, plus sine, sine. And again, you're starting with 2 angles, and you're creating basically a third angle, in this case by combining them via subtraction. Okay, well let's take a look, just see what your sheet says here, and then do a little investigation, do some examples, etc., etc. there. So it says what real numbers, or angle measures in radians, of course. So what real numbers or angle measures in radians do we know the exact trigonometric values for? Well, of course, we spent a lot of time in the previous unit sort of talking about sine and cosine and tangent, and it's all of them, as a matter of fact, of pi over 6. If I asked you for the cosine of pi over 6 or the sine of pi over 6, you should be able to tell me at this point in time. Pi over 4, that would be another one. We know the exact value. So sine of pi over 4 is exactly the square root of 2 over 2. Pi over 3, of course. Pi over 2, of course. And then I'm just going to write here, and all the multiples. So if I asked you for the cotangent ratio of 4 pi over 3, you could probably tell me based on the representations that we looked at in the previous unit. So now what we're going to do is essentially expand it a touch here, beyond the 6's, 4's, 3's, and 2's. And as you can see, just the most basic one that I'm going to take a look at initially is now we're going to take a look at a pi over 12. Obviously, what we can do is get a decimal approximation from the calculator, but is there a mathematical way to come up with that exact value? Where does that decimal approximation come from? So let's take a peek at this and see if we can put a few things together using our sole formula so far, and again, just kind of see where it leads us. I'm going to go over here for just a moment and just draw a coordinate plane. And just to rehash some ideas that have come up over the course of this unit. So in this case, here's what I'm looking for: the cosine of 15 degrees or the cosine of pi over 12 radians. Obviously, it means the same thing because 15 degrees is equivalent to pi over 12 radians. So I'm going to just go ahead and sketch that out here. Just 15 degrees would look something like that. Again, that would be pi over 12. And remember, of course, old news, but we know that every angle has 6 ratios to it. And those 6 ratios are based on the 3 components, x and y and r. So if I asked you for the cosine ratio for this particular angle, and that would be from here to here, which again would be 15 degrees or pi over 12 radians, What I'm asking for is what is the x to r ratio wherever I am on this terminal side. And so you could see it's going to be a fairly large number. I do have a fairly large horizontal in relation to that radius, the direct distance from there to there. Well, let's go ahead and take a look. First and foremost, I guess, is cosine of 15 degrees or cosine of pi over 12, is it positive or negative, everyone? Well, we are up in the first quadrant. And so I'm hoping you would certainly all realize that whatever value we end up getting here, we do know that it is going to be, of course, a positive value. Okay, now part B. It says use values that we know and the difference formula for cosine to determine the exact value of cosine of 15 degrees. So I'll stay degrees for just a second here, and then maybe we'll transfer it over to radians. But I guess I would ask you, can you think of two numbers that we know that we can combine together in order to create 15 degrees? And again, this would be using a difference. And, you know, by the way, just if it helps you, just remember, of course, I think this is old news, but I'll just put the degree equivalents down below here, just in case that's something that would be useful for you. And there are a couple different choices, a couple really nice ones, as a matter of fact. You know, these first two sort of strike me as a good opportunity that we can use these. So again, just in terms of combining a couple angles together, I'm hoping you all see that 45 minus 30 is what gives us 15. So combining two that we know to create a third that we don't know. And so what I'm going to do on my board here, and you do the same on your paper, is we're going to treat that 15 degrees as 45 degrees minus 30 degrees. That is combining two angles together, again, to create the third. Now, the way this formula works, everybody, it's not distribution here. It's not cosine of 45 minus the cosine of 30, end of story. No, it is a little more intricate than that. And so what you want to do is follow the formula up above, and the above formula says you take the cosine of the first angle times the cosine of the second angle, and then add sine of the first angle and sine of the second angle. And that's what it says. That's the formula in a nutshell. So cosine, cosine, plus sine, sine. So we're using values that we know to extrapolate further into values that we don't know. And so here's what I guess I would say. Think back to that unit circle. Have to know this really super well there. Cosine of 45 degrees, of course, is root 2 over 2. Cosine of 30 degrees is root 3 over 2. And I'm getting a plus right in the middle here, everybody. And how about sine of 45 degrees, which is, again, root 2 over 2. And sine of 30 degrees, everybody, how about a 1/2? And these are values that I can work with. Now I just have to perform the operations on them. Of course, guys, order of operations, multiplication comes before addition. So I'm going to multiply, and then I'll deal with the addition. Now I'm going to try to fit this in down here. By the way, this comes up, students ask me this. Root 2 times root 3 is definitely root 6. And so I get root 6 over 4. And then plus over here, root 2 times 1, everybody, is just root 2, and then over 4. And everybody, am I allowed to add two fractions together, especially if they do have the same denominator? Sure, yeah, let's combine them. And so, guys, I get root 6 plus the square root of 2, and then divide that by 4. I'm going to box that up as that is our answer here. And that should be the exact value of the cosine of 15 degrees, or, of course, cosine of pi over 12 radians. Okay. Now, what I would love for us to do is bring up the calculator. Let's check this out. So let me move this just over here for a moment. And here's what I'm going to do. I'm going to turn this on. And I guess for right now, I'm going to go degree mode. So I'm going to change this up. And I'll stick with that cosine of 15 degrees. So everyone, I'm going to type in cosine of 15 degrees. And I told you just based on the look there, it should be, let me make sure I've got, it didn't transfer over. So let's go do that again and hit enter on that. Okay, let's get rid of that. So cosine of 15 degrees, as I mentioned, should be a number fairly close to 1. And you can see that right there. You look at my diagram that I drew and the one that you drew, and that x to r ratio, this seems like a really good number for that. Absolutely. Now that number should be this answer right here, everybody. So let's go ahead and check it out. So I'm going to do parentheses, square root of 6 plus square root of 2. And then I'm going to divide that by 4. And lo and behold, it's that number. There it is. There's your cosine of 15 degrees. And so again, we're just using these formulas to go a little bit beyond, to expand beyond some of the angles that we saw in the previous unit. All right. Good. Well, let's do a few more problems with this. It looks like, well, obviously this whole unit is based on dealing with verifying relationships amongst all of the 6 trigonometric functions. So in this case now we're just upping the ante a little bit by changing around the inputs a little bit. In the previous section, of course, what we really saw is we just had a uniform input there. It was basically all in X or whatever the case may be. Now what we're doing, again, as I said, is kind of playing around with different inputs and seeing where that leads. So it does say here, verify the identity. And so this piece right here, which I'm going to go ahead and do, I'm going to change one side to make it look like the other side. And it says, does it look familiar? Well, let's do the problem first, and then I'll kind of ask you to think about that piece and obviously sort of give you what it is. You have seen this formula before, as a matter of fact. So when I see that left-hand side, and that's exactly what I'm going to do, guys. I'm going to change that left-hand side and make it look like the right-hand side. It is not distribution, everybody. Let's be very clear about that. This is not just cosine of pi over 2 minus cosine of x. It is the difference formula for cosine. And that says take the cosine of the first, cosine of the second, plus in the middle, sine of the first, and sine of the second. That's what it says. And so if you kind of take a look at this piece, a couple of these are constants, as a matter of fact. You have a cosine ratio of a particular angle in radians. I know this one. Cosine of pi over 2, everybody, is 0. And think back to the unit circle if that's not clicking for you. And then so I have 0 times the cosine of, again, our variable here, and then plus on this end, sine of pi over 2 times sine of x. Well, of course, everybody, we do know also sine of pi over 2, at the top of the unit circle, the sine ratio is going to be 1. So I have 1 times sine of x. And so as you can see, everybody, what happens here when I do 0 times whatever this is? Well, that's just 0. So this cancels out. And then I have 1 times sine of x. I'm hoping you're okay with me skipping maybe half a step there. But basically, I bring that other side down, and I've certainly verified it. Okay. Now I am curious, because it's oddly enough, you have seen it before. I would probably say that you saw it more because it was in right triangle trig. You saw that as 90 degrees as opposed to pi over 2. So I'm just wondering if you happen to recall that. And it says, does it look familiar? Think about right triangle trigonometry. As a matter of fact, it was kind of day 1 of right triangle trig, when we were just developing ratios in a right triangle. And we saw an interesting relationship, and we actually saw some of the names finally coming together a little bit. Okay, well, let's see. Let's tell it to you. It was sine and cosine. Do you remember the relationship that they have? Sine, cosine. So sine and cosine, one angle, and its complement. And so if you remember correctly, just to get this moving along for you, this is what's called the definition of cofunctions. And what it basically said is cofunctions of complementary angles are equal. And that's what we have exactly here. Sine and cosine are what are called cofunctions of one another. And x and pi over 2 minus x are complements of one another. So just last time here, cofunctions of complementary angles are equal. And we just proved that using this difference formula for cosine. Okay, great. So again, nice and straightforward there, just applying that and I evaluate the constants and then just perform the mathematics with the variables. Okay, let's do 2. So verify here. Now I like this one. Think of all that's going on here. I have 3 different inputs. I have an alpha and a beta and an alpha minus beta. And I have, let's see, 4 trig functions also related together. So 3 different angle measures, or 3 different inputs, and 4 different trigonometric ratios. And apparently the left-hand side for any values of alpha and beta are equal to the right-hand side for those same values of alpha and beta. Let's show it, guys, of course. So first order of business is to try to make some of these inputs a little more uniform, so I can clean this up and get them back into their original 2. So I can get it just back into alpha and in beta, and that's what I'm going to do, everybody. So, we did it now. This is the 3rd time. It's cosine of the first, cosine of the second, plus sine of the first, sine of the second. So that's what cosine of alpha minus beta is. And then I have this piece right here, sine alpha, cosine beta. Can't really touch that at this point in time. Now, I don't see any identities out there because everything is just in its basic cosine and sine form. They're all just now 2 different angles, independent of one another. And so how are we going to pull this off? Look to the other side. I need cotangent, which is, cosine over sine, and I need a tangent of the other angle, which is sine over cosine, plus right in between the 2. So I see this, and guys, it almost seems like a split would be a good idea here because they're split on the other side, and that's what I'm going to do. I'm going to split these up and see what happens. So let's see, I've got cosine, cosine over our common denominator. We saw this as one of the algebraic techniques that could potentially come up. So putting together fractions and taking apart fractions. Absolutely. Just good algebra there. So let's see this, and let's see if that was the proper move. So now it's at least looking, just in theory, like the other side. Now I need to make it exact. Well, if I take a look at each individual fraction here, everybody, I'm hoping you all agree that is a common factor. So slash and burn that one. And then what are you left with? Cosine of alpha over sine of alpha. And lo and behold, guys, that's what this is. So there's my cotangent of alpha. Here's my plus in between, everyone. I look to the right-hand side here, and sine of alpha is 1 on top, 1 on bottom. Slash those as well, and I get sine of beta over cosine of beta. And as you can see, of course, that's tangent of beta. So now 2 different angles kind of related together here. And let's bring that on down. And we've got a winner. Okay, so all sorts of identities. Again, the last section, it was all just 6 trig functions, uniform input. Now, everybody, all our trig functions, but in here, it's 3 different inputs. 1, 2, 3 different inputs there. Excellent. Well, let's keep it going. Okay, so now this is, again, the beauty of these notes worksheets, of course. Rather than you having to copy them down, I took the time and printed it out for you. But these are the first 4 out of around a dozen that you will have to, again, learn / memorize there. It looks like number 2 is the one we've already seen and played around with that a little bit. So there it is, difference formula for cosine. And there it is in all its glory. Now you see up above it the sum formula for cosine. And notice it's very similar. That's the good news with these. They're not totally different and unique. They're just slightly modified from one to the other. So the cosines very close together and the sines very close together. I'll just sort of give you a heads up as to how I think of them, and you can kind of take it for what it's worth. If you like it, great. If you don't like it, hey, that just, you won't insult me by any means. But basically, you're going to have to know these 4 right here. So the way I kind of pair these up, and you can see they are pairs here, 2 and 2. In this case, I know for cosine, I think of it as it's the same ratio. So in terms of the pairs, same ratio, cosine and cosine, and in this pair, sine and sine. That's what I mean by same ratio, opposite symbol. So again, feel free to write this down or not. It's just a way that I remember them. But as I said, take it for what it's worth. So for example here, when I think of the cosine ratios or the cosine formulas for sum and difference, I know that the pairs are the same. So cosine and cosine and sine, but the symbol is opposite. So the sum formula has a minus symbol, the difference formula has an addition symbol. So same ratios together, but opposite symbol. Whereas the sum and difference formulas for sine, here they are, guys. Here the sum and difference formulas for sine are the exact opposites. They have opposite ratios paired and the same symbol. Sum plus, difference minus. So I just reverse it for these two guys. I say it's the opposite ratios that are paired, one sine, one cosine, and it's the same symbol. Hope that helps. One way or the other, I'm afraid you are going to have to know those. And let's go ahead and at least utilize them, maybe just accessing them a little bit and kind of getting comfortable with that piece might be helpful. We'll have to see. Okay, so I just have a problem set here, several examples out, and we'll just go ahead and take a look at those. And again, there's a day 2 to this, which we'll explore some other types of problems as well. But for right now, let's just go with the comfort level on these 4 formulas. So it just says evaluate cosine of pi over 6 plus pi over 3, and then cosine of pi over 6 plus cosine of pi over 3. Are they the same? Now, I believe I've implied the answer to this already. But let's do it. Let's see what happens. In fact, let's just go ahead and draw a little vertical curtain here. And let's do our formula first. This, everybody, I'm hoping you realize, is the sum formula for cosine. Now, I'm actually going to apply the entire formula here, and then I'll show you a slight shortcut to this after the fact. Sorry for doing it after the fact. But I'm going to go ahead, because, again, we need some practice with it, and say, okay, well, this is cosine, cosine, minus sine, sine. So it's the top one, guys. Cosine, cosine, minus sine, sine. So what I mean by that, everyone, it's cosine of pi over 6, cosine pi over 3, opposite symbol, everyone, and then sine pi over 6, sine pi over 3. Now these, you just know. From unit circle and beyond, you know that the cosine ratio of pi over 6 is root 3 over 2. Cosine of pi over 3 is 1/2. Minus, and then you end up getting, interestingly enough, sine of pi over 6, which we do know is 1/2, and the sine of pi over 3, which happens to be root 3 over 2. Again, you know those values. So you end up getting root 3 over 4 minus root 3 over 4. And everyone, I know this seems a little odd here, but the bottom line here is I just have that minus itself, hoping you all see, of course, that that's going to be 0. Wonderful. Now, just FYI, cosine of this is definitely 0. By the way, again, just in terms of the shortcut, I'd be negligent if I didn't at least show you here. These are two numbers that we can add together inside the parentheses. Pi over 6 plus pi over 3, well, this is 30 degrees and 60 degrees, which would make 90 degrees. Or in terms of pi over 6s, everybody, this would be, let me see if I can catch this right here. Oh, yeah, this would be 1 pi over 6, and this would be 2 pi over 6 for 3 pi over 6, which is pi over 2. And guess what, of course, is the cosine of pi over 2? Well, cosine of pi over 2 is 0. So it works out either way there. Okay, now what I want to know is, can you just go ahead and distribute and get this right here? I think, again, I've already sort of implied that, but let me show you that that's not going to be the case. So cosine of pi over 6 is this. Cosine of pi over 3 is that. You add these together, and that's what you get. Is that the same as 0? No, of course not. And so a big fat no right in there, please. So I'm just hoping nothing more here for this example than knowing that don't distribute. It's not the same. It's not even close. Okay, let's keep going. Alrighty, so I'm going to stay radians here for a little bit, but we'll correspond it to degrees if need be. Now I'm just thinking here we can do both of these if well, we'll just see how I feel after example 4 and see if it's necessary. But you notice it's the same type of problem. So first and foremost, it is helpful to understand, well, sine of 7 pi over 12, well, remember everyone, 7 pi over 12 is really 7 15s. So remember, every pi over 12 radians, as we saw at the beginning of this lesson, is 15 degrees. So if I asked you for the sine of 7 pi over 12, in terms of its degree equivalent, that would be 105 degrees. So that's essentially what I'm asking for. As I said, I'm going to stay radians, but I think it's helpful at least to know your degree measurements there to build some combinations. So here's what I'm thinking, long story short. Let's come over here. Let's do this here, and then we'll go forward in radians. Can you think of two angles that we know? All the trig ratios on, two angles that we're very comfortable with that will somehow combine together to get 105. So think again, 30s, the 45s, the 60s, the 90s, etc., etc. To combine them together in some way, or any of their multiples, by the way. It works with multiples as well. Multiple ideas. I would argue probably that a 60 and 45 is the one that would come to most people's mind first. 60 and 45 make 105. So just in terms of getting my bearings in degrees, 60 and 45 combine together to give us 105. And so when I go ahead and do this now in radians, which I do want to do, that should be our comfort zone, what that is basically going to transfer over to is sine of pi over 3 plus pi over 4. Hoping everybody sees that. So again, this just helps me, this right here, helps me get this piece right here. That's what I'm after when I say sine of 7 pi over 12. Pi over 12 is really pi over 3 plus pi over 4. So what I'm doing is combining two angles together that I know a lot of, and a lot about, I should say, sorry, to get a third angle. So I'm hoping everybody is in agreement that this is some formula for sine. Some formula for sine. And so as a result, I go to the top and I say sine of the first, cosine of the second, and then plus cosine of the first and sine of the second. Okay. Now these we just run with, everybody. So root 3 over 2. Cosine of pi over 4, of course. Root 2 over 2. Plus in between. Cosine of pi over 3, 1/2. Sine of pi over 4, root 2 over 2. Okay, guys. And you see a very similar one to one we've explored before. But I end up getting this. Oops, sorry, that is a plus. And so I get root 6 plus root 2, and all of that is over 4. You end up getting that same value that we got for the cosine of 15 degrees. And I just like to make visual connections. You don't have to write this on your paper, but 105 would, be basically right here. And so what we're looking for when I say the sine of 105, the y to the r. And you can see the y to r has a very, very similar look to the x to r of that cosine of 15 degrees. And again, it shouldn't come as a surprise. We've seen patterns with all of the pi over 4s, the 3s, and the 6s. Of course, you're going to see patterns on the pi over 12s. Will it always be this exact number? No, no, no. So be careful with it, please. Okay, good. Let's do example 5. Let's take care of this. So everyone, I'm going to do sine. And again, it just helps me. When I say negative 5 pi over 12, so every pi over 12 is 15 degrees. I have negative 5. So I'm seeing this negative 5 times 15 is negative 75. So that's basically what it's asking here simultaneously. The sine of negative 5 pi over 12 or the sine of negative 75 degrees. Again, I'm going to stay radians, but it just helps me in terms of combining angles together to go degrees initially. So this is a good one. Try to combine a couple angles together to get down to negative 75. I think we're going to have to start with the negative angle to begin with, a clockwise rotation, so to speak. Then from there, we can go further. So first and foremost, what I'm seeing this as, everybody, is this is the angle right there, negative 75 degrees, give or take. What's that sine ratio? Of course, well, you can do this a couple different ways. If you are ahead of me, and you come at it with a couple different numbers here, it does work out the same. So I'm going to let my a value be negative 45 and then minus 30 degrees. So A is going to be negative 45, B is going to be 30, and I see it as the difference of the two. Again, there are different ways to pull this off, everyone. So if you come up with a different way, as long as it combines together and you use the right formula, should get it to work. So let's go with it here, everyone. So I see difference formula for sine, the way I've presented it. And so sine of the first, cosine of the second, keep the symbol, and then it's cosine of the first, sine of the second. That's looking good. Alrighty. Well, just a clockwise rotation here shouldn't scare us. Sine of negative 45 degrees happens to be negative root 2 over 2. Cosine of 30 is going to be root 3 over 2. Oh, and I should have gotten radians on this. I didn't, but that's okay. It'll still work out the same. So, you know, on the last one, example 4, I did write it in radians, and I said I was going to do that here and then forgot about it, but it's going to still work out just fine. If you want to stay degrees, as long as you have it equivalent, you're going to be fine with it. These are the ratios that matter right here. Okay, and then minus cosine of negative 45 actually happens to be just root 2 over 2, and sine of 30 is 1/2. So I get negative root 6 over 4 minus root 2 over 4. Sounds good. A couple different ways we could probably write this one. I don't see any real need to do anything dramatic there. So something like that would be fine. So you notice the same numbers, obviously, but in this case, sine is going to be negative down in the fourth quadrant here, and so as a result, that has to occur with these numbers. Okay, so one, I went back to radians. One, I stayed in degrees. It just helped me at the time. So be it. Well, let's wrap this up with just a couple quick identities. This one just happens to be very similar. Again, just getting comfortable with these formulas at this stage. This I see as, by the way, again, another definition of cofunctions. Looks like I threw 2 on this one. So sine, cosine, and then x and pi over 2 minus x. Cofunctions, complementary angles, are equal. Well, let's change that left-hand side. So difference formula for sine, guys. By now, you're looking at the top of the page, and you're starting to run with it a little faster. I would say it's sine of the first, cosine of the second, and then minus cosine of the first, sine of the second. And that looks pretty good. Constants in there, everybody. You know this. You know the sine of pi over 2 is positive 1. So I have 1 times that. And you know the cosine of pi over 2. It is 0. And so I have 0 times this. Well, 0 times that, that's going away, guys. Say goodbye to that piece. And how about cosine of x right there? And there it is. Nice and quick. So basically, on this notes worksheet, I've put 2 different definitions of cofunctions. And from both perspectives, of course it works. We saw that when we did right triangle trig. All right, last one here. Example 7. Let's see. Verify. Now I've got 4 different inputs on this one. That's kind of cool. So I have a plus b, I have a minus b, and then I have both the originals, a and b. And they're the ratios that would go together with those 4 different angle measurements. Well, let's see what happens here. You know, I'm feeling that we're going to take a look at that left-hand side, and see what happens on that left and make it look like the right. So guys, I see this. Sum formula for sine. Sum, sine. So sum formula for sine says sine of the first, cosine of the second, keep the plus, cosine of the first, sine of the second. Okay, so just like above, opposite ratios, same symbol. Now a plus right in between. Here's the plus from here to here. And then let's tweak this. Let's expand it out. Same idea. It's sine of the first, cosine of the second, and it'll be minus cosine of the first and sine of the second. All right, good. So that's all I did. I just expanded it. Nothing special at all. I'm just applying the formula. And from what I see, everybody, take a look at what we have. We do have sine A's, cosine B's. We also have cosine A's, sine B's. It looks like in terms of this one, everybody, I hope you see it, there's one plus and one minus there. So I think they're going to go away. And then take a look, I've got two positives of this expression. This plus this is obviously two of them. And that's pretty quick, huh? All right, 4 formulas that you're going to have to know, everybody. And that's a good starting point. There's obviously kind of a day 2 with this that we'll go ahead and explore some different types of problems. But this is a good start. So work with these types on the individual practice problems there. And please ask questions if you have them. And as always, I certainly appreciate you listening to the lesson. And let me know if there are any questions.